Hello. In this video, I'm going to build a 2-bit adding logic circuit using a couple of gates. But before I do that, I'm just going to review the gates and what they do, and also go into a little bit about binary. So just to first review the gates, first gate that's important is a NOT gate. A NOT gate is an inverter gate. You input 1, you input 0, you get an output of 1. You input 1, you get an output of 0. So whatever you feed into it, it will feed out the opposite. Now remember, the AND gate needs both of these inputs to be 1. So when both of these inputs are 1, the output is 1. At all other times, the output is 0. The NAND gate is the opposite of an AND gate. It's literally an AND gate followed by a NOT gate. So whatever this output is, it is inversed. So we have 1, 1, 1, 0. When both of the inputs are 1, the output is 0. An OR gate is an either, really, OR gate. So when any of the input is 1, the output will be 1. Okay, no inputs of 0, we get an output of 0, but if either of these is on, then we get an output of 1. The NOR gate, again, is an OR gate followed by a NOT. It will be the opposite of this, so it's only on when both of those are off. At all other times, it is 0. It is an OR gate followed by a NOT gate. And then the exclusive or the XOR gate. Now the XOR gate is literally if someone tells you you can have a chocolate bar or a packet of crisps. You don't take both. So 0, 0, output is 0, and when one of these is 1, you get an output of 1, but when both of them, that again is an output of 0. Okay, so we're going to use a selection of these gates to make a circuit which will add two binary numbers together. So just to go through binary numbers, I've here a input board from the EduCat.ninja logic kit. We can use this to model sort of binary numbers, and this is exactly what happens inside the computer. Okay, so for the first one, we need to assign what these are. So the first one is, it's actually, binary is 2 to the power, is base 2. So this is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. So what that means is this input is 1. Here we have 2, 4, and 8. So with these 4 bits, each one is called a bit, you can assign a number, they represent a number. So if we have this number, if we have 0, 1, 0, 1, that means we have a 4 and a 1, so that will be equal to the number 5. Okay, if we have 1, 0, then that will be equal to 2. If we turn them all on, so that would be 1, 1, 1, 1. That's going to be 8, 4, 2, and 1. So that's a total of 3, 7, 15. And finally, if they're all off, that is, of course, 0. So with 4 bits, you can represent any number between 0 to 15. Okay, right. So let's talk about adding these inputs together. So what we can use a second input board for the two inputs. So we'll add these two inputs together. So what we need to do so let's look at what the output will be. So the options are, well, if we add 0 and 0 together, we want an output of 0. If we add 0 and 1 together, we want an output of 1. If we add 1 and 0 together, we want an output of 1. And if we add 1 and 1 together, we want an output of 2. But we need to represent this in binary, so that is going to be 1 and 0. So the output will be 2 bits long. So let's look at the input and output. So if we have the two inputs, we just need one input. So the input A is going to be here, so input B is going to be here, but the output is also going to have two outputs for that. So let's draw the truth tables that we are looking for. So let's concentrate on the answer bit, and the carry bit we will deal with a little bit later. With multi-bit additions, this will be carried over to the next one in the same way as if we are adding 28 to 17. 8 plus 7 is obviously 15. We carry the 1 over, and that's going to be 5. So that will give you an answer of 2 plus 1 plus 1. So 28 plus 17 is 45. So with 2 or more bit additions, we need to have a 3 inputs, but we're just going to deal with adding single bits together to give you a maximum of outputs of 2. Okay, so the truth table for the answer bit will look like this. When we have an input of 0 and 0, we want our answer bit to be 0. When we have inputs of 0 and 1, we want our answer bit to be 1. When we have an input of 1 and 0, we want our answer bit to be 1. And when we add 1 and 1 together, we want our answer to be 0. Okay, and hopefully you can see that that is represented by an XOR gate. So if either of those is 1, then the output is 1. If both of those is 1 or both of those is 0, then it's 0. So we're going to need to use an XOR gate in order to make this 1-bit or half adder, as it's called. Okay, now let's have a look at the other logic gate that we're going to need. When we have our same inputs, 0, 0, 0, 1, 1, 0, and 1, 1, we are going to need the outputs of 0. So looking at this bit now, 0, 0, 0, 1. So the other gate we're going to need, is going to be, hopefully you can see that that is going to be an AND gate, because the XOR gate is 0, 1, 1, 0, and the AND gate gives us 0, 0, 0, 1. Okay, so let's start to put this together with our AND and our XOR gates. So now the very first thing we're going to need is we're going to need to split these signals. So what we're going to do is we're going to use these two power input boards to add the first signal to the second signal, just as if we add two numbers together. I'm going to represent them as signals from the two separate boards. And my other signal splitter is here. So this is going to be our first signal, and this is going to be our second signal. Okay. So we are going to need to put into the AND gate, and we're going to have the XOR, so we're going to represent the output here. So the AND is going to be here for the carry bit, and the OR and the XOR to be here. So this is going to be the output answer bit, and this is going to be what I'll call the carry bit. So what do we need? We need the XOR. We need to feed in the input from both of those into the XOR to give us the answer bit. So let's just test that. 1, 1, 1, 1. So 1, 0 gives 1, 0, 1 gives 1, and if they're both, it's off. So all okay so far. Now, just need to connect the other wire to the AND gate, and let's see if that's working for us. Okay, so this is literally the circuit, the half adder circuit. So this will add these two bits together and it will output our answer. So if we add 1 and 0 together, we're going to get 1. If we add 0 and 1 together, we're going to get 1. Obviously 0 and 0 is 0, so good. And if we add both of them together, we're going to get 2. So that is the half adder circuit from first principles. You've got your two inputs, you need to split the signal, and then you have your AND for the second of the carry bit, or the higher power of 2, as it were. So 2 to the 0 and 2 to the 1. So 1, so 0, 1, 1, 2, 2. Okay. And that is the simplest adding circuit. So let's draw that circuit in sort of standard notation. So what do we have? We have our two inputs, A and B. Those are the two bits we're adding together. We need to split them both, and then we need an XOR gate. Now, an XOR gate has this double curve here, and we're going to need to feed the input in from the first one and the second one, and then for the output, we're going to need the AND symbol, and we want that to come and give us our first bit, and this will be the carry bit. Okay, and that hopefully you can see is what we have here. We have our output from the XOR as the answer bit, and this is the higher power. So this is the 2 to the 0 and 2 to the 1. So if A and B, this will give us 0, 0. Okay, input 0 and 0. We've got 0. If we have 1, technically, let's do it this way. 1 and 0, we're going to get 1. 1 and 0, we'll get 1. And then if both of those are added together, we're going to get 1, 0. Okay, let's just go through that again. So our 2 output bits, we've got our last bit, which is based on XOR, and we've got our penultimate bit, which is based on AND. Okay, and that is a half adder circuit. 0, 0 gives you 0, 0. 0, 1 gives you 0, 1. 1, 0 gives you 0, 1. And 1, 1 gives you 1, 0. Okay, that is the half adder circuit. Okay, thank you.